Hello, welcome to lecture number 25. In the previous lecture, we derived the dispersion relation of Rossby waves, which are planetary scale waves. Now we'll see the phase speed of these waves. So we'll see how the expression for phase speed. So the phase speed of a wave is the frequency over the wave number. So for Rossby waves also, because it's a wave, we can define a phase speed. So first of all, this is going back to basics. So what happens is that in meteorology and oceanography, we need to choose a coordinate system to define the velocity directions. So this is the Earth, and most commonly the velocities along the direction, along the latitude, along these imaginary lines that we call latitudes, which is in the direction east, let's say at this time instant, is one component of the velocity, and the other component of velocity is along north. This is along lines along the longitudes. So this velocity along the east direction is also denoted by the variable u, and this is called the zonal velocity. And this direction is most commonly taken as the positive x direction. This direction is necessary because we'll be using this direction for to represent the phase speeds, and the flow along the longitudes in the positive, in the northern, the north direction towards north is the positive y, and this is represented by the variable v, and this is called the meridional velocity, and this is the positive y direction. This terminology may appear in our discussion, and hence this is important for us to clarify at the beginning of the lecture. There is meridional velocity and zonal velocity, and this you will frequently see in the literature related to these fields. So positive is from west to east, and the in the north-south direction, the positive is from south to north. There is one set of terminology that also we need to understand. So this is called these are named based on the direction that they're coming from. And for example, if there is an easterly flow, this is coming from the east. If there's a northerly flow, coming from north. So this is for both oceanic flows, atmospheric flows, so northerly wind, easterly wind, and the zonal velocity is positive if this is a westerly flow, and the meridional velocity is positive if this is a southerly flow, because of the fact that southerly flow means it's coming from the south, and westerly flow means it's coming from the west. So it's going from west to east and south to north. So these are positive directions. This is by convention. Of course, you can define your own coordinate system, you can define your own directions, nothing can stop you, but this is just a convention that we are going to use. That makes it's easier for to and helps in consistency. It's easier for analysis. Okay, now given the fact that we have cleared up some basic terminology, so we look at the zonal phase speed. Of Rossby waves. This is denoted by Cx. This is defined as the frequency by the wave number in the x direction, and this is minus beta naught Rd squared by 1 plus Rd squared kx squared plus ky squared. Now where does this come from? Because this comes from the dispersion relation that we have already derived, and the Rd is the Rossby radius of deformation. As you can see here, this whole term minus beta naught Rd squared by 1 plus Rd squared kx squared plus ky squared is positive, and there is a negative sign in front of it, hence the wave speed is negative. There is one more thing to remember. This is regarding terminology. So omega is frequency. Previously in the vorticity chapter we had used omega for vorticity, but that is not the case. Omega is frequency in the waves chapter. In this module, in this chapter, we are using omega for frequency. Please don't confuse it with absolute vorticity or vorticity that we had discussed in the earlier classes. Okay, so now few observations. One observation that I have already made. So Cx is negative. Now, based on my discussion, the discussion that we had in a previous slide, you can just pause and think, what does it mean? If Cx is negative, which direction the flow is, based on the terminology that we have introduced. So based on the terminology, the flow is always from east to west. Hence, Rossby waves are always from east to west. They are always propagating to the west, and we will see why that happens. We'll give a mechanistic explanation of the reason for this direction to the Rossby waves. Now, meridional wave speed. Meridional meaning along longitude. So the meridional wave speed meridional phase speed is given by Cy, and this is defined by the frequency over the meridional wave number, and this is minus beta naught Rd squared kx divided by ky 1 plus Rd squared kx squared plus ky squared. Okay, now you can see that this determining the sign of this velocity, this component of velocity, is not easy, because it depends on kx and ky. Unlike in the previous case where there was no dependence on kx and ky because of the fact that kx appeared in the numerator and we divided it by kx. Here kx appears in the numerator and then divide the whole system by ky to look at, to find out the magnitude of the meridional phase speed. Hence this sign is indeterminate. So any direction of travel is possible. So in the meridional direction, the Rossby waves can go either in the north or to the south, whereas in the zonal component it is only going towards the west. Hence the Rossby waves can propagate Rossby waves can propagate northwestward, southwestward, and westward, given that this is the choice of coordinate axis that we have. Because the meridional velocity is indeterminate, it can be in both the directions, whereas the zonal velocity is determinate, or that is only in the western direction. It's always negative. Hence, this can propagate in northwestward, southwestward, and westward direction. This does not have an eastward component. So now, again, another observation: if if 1 over kx and 1 over ky are much larger than the Rossby radius of deformation, that means the wavelengths in both the directions, that is kx and ky, are much larger than the Rossby radius of deformation, then we have C equal to minus beta naught Rd squared. Because from the wave speed calculation, if we put the limit kx ky goes to 0, we get this limiting phase speed in the situation where the wave numbers are very small, that is the wavelengths are very large, and very large meaning with respect to the Rossby radius of deformation. Hence the observation that very large waves, so okay, we can immediately see a difference here. So we have Cy, which is dependent, let me use a different color. So it's Cy is dependent on kx, ky. So these are the functional form of the in which the Cy is dependent on kx and ky. Similarly, Cx is dependent on kx and ky. That means the waves are dispersive. Okay, the phase speeds, the speed of different waves, meaning waves of different wave numbers, are different. Whereas in this case, this is a peculiar condition in which the waves are very large. Here, very large waves are non-dispersive. Why it is non-dispersive? Because there is no dependence of wave numbers on the the phase speed does not depend on the wave numbers. That is, it's equally, all the wavelengths, if they're large enough, then the Rossby radius of deformation, they propagate at the same speed, which is minus beta naught Rd squared. So they are non-dispersive, and because it is non-dispersive, they preserve their shape. So this dispersive wave loses their shape, they whereas non-dispersive waves preserve their shapes. Now, this Rossby radius of deformation could be of the order of few thousand kilometers in ocean and atmosphere, and then we can get an approximate idea of the phase speed of these Rossby waves. And Rossby waves can be both baroclinic and barotropic. So we are discussing only barotropic waves. The baroclinic waves move very slowly. Barotropic waves have a much larger speed, and baroclinic waves depend on the structure of the stratification. So we are not going to do that, but they move very slowly in the ocean, approximately a kilometer a day. So this is about Rossby waves. Now we'll get to an interesting kind of waves called topographic waves, and so this is also a barotropic wave, meaning it does not depend on the vertical structure of the stratification. The reason why we are doing this is also because this is similar to the Rossby waves, and we'll show how both of these have similar mechanisms for formation, and this topographic waves is something that is easily generated in laboratory experiment. Hence, it is important for us to know if we want to study effect of beta plane, effect of variation of Coriolis parameter. We get similar kind of waves here, and we can use this to study large scale Rossby waves, because of the fact that creation of a variable rotation system in lab is very difficult. So let's start with topographic waves. As the name suggests, this is generated in the because of the fact that the topography is not uniform, that is, the ocean is not flat, and that is all, I mean, that is well known. The ocean has multiple hills and valleys, and these waves are generated due to the non-uniformity in the ocean bed. So these waves are generated due to non-uniform topography. So we keep even if we keep f constant, the planetary vorticity as constant, we see that a weak bottom gradient gives rise to planetary wave similar to the beta effect. What is beta effect? Beta effect is when the Coriolis parameter or the planetary rotation is varying linearly. Okay, so these are generated due to topography, and hence let's draw a schematic of the problem. So let's say we have a free surface, and then we have a the bottom, I mean a reference level, I mean reference state is this one. There's a reference line that I have drawn, but the main important thing, I mean, is the topography. So there is a slope which is like this. So this is the direction k cap, this is the direction j cap, and hence the direction out of the plane of the paper, out of the plane of this screen, is the I cap direction. Now at a location y from this origin, I mean this location is the origin, hence any distance is being measured from here. So any direct, I mean along the j cap direction at location y, the depth of the topographical feature, this bottom slanting feature that you see here, this is the bottom topography. To note that this is slightly slanting, this is not very steep. Okay, there's a weak gradient. So the other variables of interest, so once we have this one, we can define the other variables. So h is the total height of the water column, and from the bottom topography to the surface of the ocean. So this is the surface, this is the ocean surface, and this is oscillating, and the dotted lines are reference lines. Okay, this is kind of a time averaged value, let's say, and this is the displacement from a reference level. This is eta, and this is h naught. So in this case, we have the total height is equal to h naught plus alpha naught y plus eta. Alpha naught is the slope, so alpha naught y is the distance after we have gone to this y location, and this is y is at any point that we are measuring. Okay, so alpha naught is the slope, and here another point to mention here is that the I cap direction is the along shore direction, and j cap is across shore. What is shore? It's the, I mean, you know, the shoreline. So along shore is, it is, so let's say you have a beach and you have the ocean here. So along shore is along the shoreline, along the beach. Across shore is towards the ocean. Here we are going into deeper ocean. So this is towards the positive j is where the ocean lies, and I gap is along the shore, and this is also along isobath. So the bathymetry is assumed to be same along this one. So that means this figure extends infinitely in out of the plane of the this screen and into the screen. That means anything that we are coming along the positive I or negative I, or positive I cap and negative I cap are at the same height, and hence the term isobath. Iso meaning same. Okay, so h naught is the reference, mean reference depth. Alpha naught is the bottom slope. So eta is the free surface displacement. The bottom slope is assumed to be gentle, and this is what we started with. So let's see. Assumption, this quantity alpha naught L by h naught, so L is any characteristic length scale, is much less than 1. So length scale along the x direction. Okay, that means the change in the slope with respect to the total height of the water column is very small. So here one interesting thing to note, and we are building an analogy with the Rossby waves that I said. I said that we are doing this to see how it's similar to Rossby waves, and this similarity will help us in, as I mentioned, it helps us in creating experiments, and the similarity also helps us in understanding the mechanics behind the formation of both of these waves. So here alpha plays a role which is similar to the parameter beta in the planetary wave or the Rossby wave in the beta plane approximation, So this alpha plays a role similar to beta in the beta plane approximation. So alpha is also called the topographic parameter. Okay, we'll see more analogies. We'll see how our why do we say this looks similar further as we go along in into developing the system and looking at the dispersion relation. We will have to gather first the governing equations. So we'll start with the vertically integrated the continuity equation, and we'll use the full set of barotropic equations to see how dispersion relation of these topographic waves look like, and then we'll see how actually the analogy builds between the topographic waves and the Rossby waves. So this is where we stop. We'll do the derivation of the dispersion relation in the next class. Thank you.